Welcome to General Chemistry 1. My name is Mr. Ferguson, and this is General Chemistry 1. I am passionate and I'm excited. It is a treat for me to be your professor this semester. General Chemistry 1, it provides a basis and a foundation for analytical chemistry, biochemistry, organic chemistry, and physical chemistry. General Chemistry 1, it gives you the skills, tools, and acumen that you need to pursue your future careers. General Chemistry 1. My name is Mr. Ferguson. I am an adjunct faculty member at the University of Bahamas. Just before we get started, I want to remind everyone, you are not alone. This is an academic community. Remember to get help when needed. Reach out to the university services if needed. Never give up. Keep trying. We are here to help you be ethical, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. So a little bit about me. I am a value-driven individual. I want to make value-driven impact in society using science principles. Some of my values are respect, integrity, and excellence. I expect those values to be exhibited in this class this semester. As I said earlier, I'm a adjunct faculty at the University of Bahamas. Some roles I've served in, I've served as a graduate student. I've served as a Bridge Fellow, graduate student at Indiana University Bloomington. I have served as a Bridge Fellow with one of the largest scientific societies, the American Chemical Society. I have also served as a GEM Fellow with the National GEM Consortium. I have served as a podcaster for The New Chemist, the co-host of The New Chemist, as well as an author for several books. Lecture attendance is mandatory. At this time, lecture will take place via Zoom. Class assignments will be placed on the online platform. If similar information about the class is lost for the first instance, we can arrange for another copy. After that, correspond with your classmates. A lot of the information that is provided this semester will be provided electronically. Summaries of lecture notes will be uploaded and provided. My goal is to make this class as engaging and enjoyable and cognitively stimulating as possible. The course textbook is Chemistry: The Central Science by Brown, LeMay, Burstein, Murphy, Woodward, and Stoltzfus. Students in this class at UB North, an electronic version of a chemistry guidebook will be gifted at no cost. It is up to you whether you use it or not, as well as supplementary notes and problem sets will be provided at no cost. Office hours will occur via Zoom. Office hours will occur. Try not to fall behind to make the class for you a more enjoyable experience. Regrading is not the ideal scenario, but if needed, it can occur. The grader and I will discuss any possible regrades, and it will be reassessed entirely if a regrade opportunity is granted. Also, a two-page justification of why must be written and emailed to the professor. There will be 3 exams, each worth 150 points. Each exam will be 50 multiple choice, each worth 2 points, and there will be 5 short answers, each worth 10 points. The dates for the exams are September 21st, October 26th, and November 23rd this semester. Only medical absences approved by the university are allowed. Any other absence will be a 0, and you can drop your lowest grade. Look at the syllabus for the dates. Quizzes will be given at the beginning of the week. Each week, they will be released electronically. This starts August 29th. If this changes, I will let you know. And it ends November 21st. These dates are subject to change. Quizzes will be 10 questions, each worth 0.5 points. The points will be added at the end of the semester. At least 70% on all the quizzes is equivalent to the addition of 1% to your overall grade. That's the equation to calculate what percent will be added to your overall grade. There is UCI OpenCourseWare. These lectures can be found on YouTube. There is MIT OpenCourseWare. Those are available on YouTube as well. There's Khan Academy. I will provide learning casts, the equivalent of a podcast, but it'll be specifically for UB North students in my class with the class content in a creative format. The link will be available on a YouTube channel page. Students, when possible, should become familiar with the various withdrawal and drop dates noted by the University of the Bahamas. This is your responsibility. All withdrawals are handled by the registrar. The last date for an automatic grade of W is determined by the registrar. So 1,050 points equals 100% of the class. There's the equation to calculate your grade. Collaboration and teamwork is allowed on homework. However, for the Google form with the electronic version of the homework set, a requisite hard copy picture will be mandatory for homework submission. Essentially, when you submit your homework, a hard copy of the written version of your homework is going to be required to be uploaded to submit your homework and for it to be graded. Some of the topics we will talk about this semester. We will talk about wave-particle duality of light. That's just a fancy way to say light exists as a wave and it also exists as particles. And those particles are quantized as photons. We will also talk about atomic spectroscopy and line spectra. So the different types of line spectra. We could go on, we could talk about the Balmer series, the Lyman series, the Paskin series. We can also talk about different models of atomic spectra with the Bohr model. And I'm going to show you a nice creative way I came up with you to practice writing your Bohr model structures. We will have a problem solving session. And that will be the exam. We will discuss the Bohr model by Niels Bohr and orbital diagrams. We will discuss Lewis structures by Gilbert N. Lewis, molecules and polyatomic ions. We will discuss resonance structures. So those three topics right there, they kind of give you a foundational basis to the Bohr model, Lewis structures, and resonance structures. They give you a basis for understanding chemical reactivity and chemical reactions. We'll discuss that later on. So for the week of October 10th to the October 14th, we will have problem solving sessions. On October 10th, there is no class. However, during the week of October 10th to the October 14th, on the Wednesday of that week, there will be an exam. So you can use that no class day to catch up on homework, relax, and prepare for your exam. For the weeks of October 17th to the 21st, and October 24th to the 28th, we will discuss thermodynamics. We will discuss thermochemical equations, explain exothermic and endothermic processes. Those are some of the things we will discuss. We'll also discuss in the ensuing weeks thermochemical equations, Hess's law, Born enthalpies, the Born-Haber cycle, which is basically a named description of how ionic compounds form in which they transition or change states. And in the process of them changing states, they are ionized, and those ions combine together to form a crystalline lattice. And then we will have a problem-solving session and exam 3, and then we will have the final exam. So if you feel overwhelmed from just this, be encouraged. The goal is not to make you feel overwhelmed. The goal is to help you to succeed and give you the capacity building experience that you need to be the successful doctor, the successful scientist, the successful researcher, the successful professor, successful person that you need to be in this society. So we're going to review some concepts at this time. Some fundamental skills I need you to have grasped. So we're going to spend a good portion of this lecture discussing fundamental skills. I will give you problems. There will be short answers, and I will also give you problems which are equations. However, in this lecture, we will discuss the concepts. And then in the practice or in the subsequent sessions and problem-solving sessions, we will discuss how to solve the problems with heuristics and algorithms. We will discuss simple ways as to how you can understand what the question is asking and how you can solve it. And then we will discuss the wave-particle duality. So, the goal of this class is to teach the chemistry content in an engaging manner that is relevant to the Bahamian student and digestible for their understanding. So I want you to understand the concepts, practice the problems that are relevant to understanding that concept, learn more nuanced details about the concept, and then practice more complex problems that integrate the details and the fundamental understanding. So let me give you an example. Say we were talking about the Bohr model. First, I would give you the workbook I designed specifically for this class on the Bohr model. Have you practiced those problems? Understand the Bohr model was basically a description and a representation of how atoms, when we designate their energy levels as quantized states or discrete levels, that the transition of those electrons from one energy level to the other results in the release of a frequency of light, and that is characteristic and observed as a specific color. In short, levels are quantized. Those levels provide a display of light at a specific frequency when those electrons relax. And that's the fundamental concept. More nuanced details will be how does that play out when we try to describe or understand the amount of energy that is released. And that energy is equivalent to a specific frequency, or proportional rather to a specific frequency. So let's review at this time. So I'm going to walk you through this review. So okay. So everyone, I designed the guidebook with the intention of teaching the content in a creative way. And we're going to walk through this content and we're going to walk through the equations. So as we begin this class, I want you to think about how will college be different from grade school? I want you to stop and think about it. I know for me personally, college required a higher level of engagement, a higher level of time management skills, and a higher level of dedication to my studies. What do you think it requires to be successful in college? Success in college requires a number of factors, and they vary from person to person. However, one thing we know is that success requires you operating with self-discovery. So hold on a second. Let's continue. How well do you expect to do in your first few semesters here? And how do you plan to aim for that success? As a science student and a former science student, because we're all learning this here, as a science student when I was an undergrad, one of the things that stood out to me was you must schedule your time and you must manage your time well. So the important thing for you to understand here, yes, there are animations, and the animations are placed there to make this discussion engaging for you. So the important things to think about is what's your learning style? How do you learn best? Are you a auditory learner? Are you a visual learner? Do you need to write it out? Do you need to use programs like Quizlet, Kahoot, Anki? All of those things, they are important and you need to know what works best for you. If you're trying to understand what it entails for a career, there are podcasts you can listen to. There are a variety of things out there. This experience in this class will be what you make of it. I will try to give you the opportunities, the facilities, the resources for you to succeed. However, the work and the onus is on you. You must be dedicated, motivated, and encouraged to work well. So what time management strategies and group studying approaches can you use to ensure learning and academic success? So essentially, do you need to use Google Calendar? Do you need to use Outlook? Do you need to use a hard copy planner? I use both Google Calendar and a hard copy planner. You have to find what works for you and implement that strategy. Later on, we will discuss, and I will show you a video on strategy before this lecture ends. The importance of strategy. Strategy is more than just planning. It must be strategic. Now, some big ideas that this college chemistry covers, some of which we will discuss in the context of the semester. All matter is composed of atoms, and intermolecular forces and bonding explains their properties. Simply put, matter, things like solids, liquid, gases, ice, for example, is a solid, liquid, water, and gas would be water vapor. All of those things are composed of atoms. Those atoms are bonded together covalently, of course, to form H2O. Within or among those H2O molecules, there are intermolecular forces, and those intermolecular forces are hydrogen bonds. Those hydrogen bonds help us understand the physical and chemical properties of water. It's important for you to understand that. Everything boils down to the compositional units of the matter or the object you are describing. Chemical reactions involve intramolecular and intermolecular changes. Chemical reactions, whether they be double displacement, addition, substitution, displacement, single displacement, whatever the type of reaction that's being discussed or displayed, chemical reactions involve intramolecular, so we're talking about the bonding, and intermolecular, we're talking about what happens in between those molecules, those changes. So molecular collisions, molecular geometry, and the approach between molecules influences the speed of those reactions. So you also have thermodynamics and kinetics. They provide a lot of insight into physical and chemical changes. So thermodynamics is like one end of the seesaw, and kinetics is the other end of the seesaw. They are distinct, yet they coincide at points. Thermodynamics basically explains how heat and disorder plays or functions in chemical reactions. Kinetics explains how fast reactions occur and why they occur fast and what causes them to go fast, whether it be their orientation, their proximity, or their number of collisions. So equilibrium and thermodynamic parameters such as entropy, which is a fancy way to describe disorder, enthalpy, which is basically how you describe the heat energy of a reaction, and Gibbs free energy, which describes the capacity of the reaction or the molecule to do work of the reaction or to do work. And those ideas, enthalpy, entropy, and Gibbs free energy, provide insight into a reaction's thermodynamic potential, whether it's thermodynamically favorable or not. Another way to say that is whether it's spontaneous or not, or whether it will occur or it's likely to occur or not. It gives us insight into the products that will form, how fast those products will form, and those parameters also give us insight into how they form. So that's important to understand. So we will discuss in this review session, this is a review session, we will discuss MADA, dimensional analysis, problem solving, and introduction, and we'll introduce the history of some chemistry pioneers. So let's talk about the scientific method. The scientific approach to information consumption and knowledge generation involves the scientific method. So what does that mean? The scientific method is the way scientists do science. Essentially, the way they operate, the way they think, the way they practice. It's, if I was to give an analogy, the scientific method is how they operate. This figure below describes or shows an example or a version of how the process of thinking occurs for the scientific method. You have your observation, and then from your observation, whether you look at it physically, try to break it down chemically, you look at the hypothesis, which are basically your educated guesses about what is going on. And from there, you run experiments. From those experiments, you gain results. From those experiments, you gain results, and from those results, you gain conclusions. And after you've done that enough, those conclusions lead to a discovery. And discovery goes along and gives you an idea or theoretical explanation as to what is going on. And then we have our physical or scientific law. So, a critical part of nature is energy, which is basically the capacity to do work or to cause change. Those changes can be physical or chemical. Now, let's keep this in mind. Matter is anything that has mass or a definite volume. There are several states of matter, which are solid, liquid, gas, and plasma. The main states we'll discuss in this class are solid, liquid, and gas. Matter undergoes different types of changes, and those changes can be physical or chemical. So a physical change involves changes that do not rearrange the intramolecular bonding arrangement or electron configuration. So what does that mean? When you're dealing with physical changes, we're not changing the bonding, we're not changing the ionic bonding or the covalent bonding. We're not changing how those atoms are connected together. We're not changing how those electrons are configured or arranged or distributed in the atom. We're only changing from the macroscopic view. This is a simple way to put it. From the macroscopic view, we change the state. So for example, with water, a physical change for water will be melting. So when the ice goes to water, or when the water goes to a vapor, those are all physical changes. The hydrolysis or the electrolysis of those water molecules, of the atoms in those water molecules, the splitting of those things, that is a chemical change. Simply put, physical properties of substances such as ductility, physical state, appearance, so like color, texture, whether it's rough or smooth, those are the things that change when we're talking about physical changes. A chemical change, on the other hand, is a change that affects the intramolecular bonding arrangements of the chemical properties, such as the electron configuration or the chemical bonding of the substance. So when we talk about electron configuration, we're talking about how the electrons are distributed within the atom or the molecule. We'll discuss those things later. In terms of chemical bonding, we're talking about ionic, which occurs between metals and non-metals, or covalent, which occurs between non-metals, or metallic, which occurs within metals. We're talking about that fundamental level of bonding. So it requires, if you think about it, because those particles require a good bit of energy to be bonded together through these interactions that we call Coulombic interactions, because of that, we know that it requires a good bit of energy for that to occur. So that requires a specific type of change, and that is chemical changes. So let's also talk about measurements. Measurements are important in science. These values are important because they affect the data's precision, so how close the measured values are to each other, and the data's accuracy, how close are the measured values to the true value. So precision, if you were to think of a dartboard has different ranges. If you hit within the same area, if you hit all of the darts on one location of the dartboard, all of them go in one area of the dartboard, that is precision. If you hit all of them on the bullseye, that is accuracy. So some SI units. The SI units will be that are commonly discussed in chemistry: a length, which is in the SI unit of meter; time, which is in the SI unit of second; amount of substance, which is in the SI unit of mole; electric current, which is in the SI unit of ampere; temperature, which is in the SI unit of Kelvin; and luminous intensity, which is in the SI unit of candela. It's also important to remember that mass is in the SI unit of kilogram. So there are significant figures that are important. Significant figures. Some rules to keep in mind. There are 4 rules I want you to remember in this class. non-zero digits are always significant. Any zero contained between non-zeros is significant. For example, 203 or 203, the zero in between 2 and 3 is significant. Leading zeros are typically not significant. Final zeros or trailing zeros are significant only after the decimal. So these are important rules to remember, significant figures. So in this section, we will provide analysis as to how to do dimensional analysis calculations. So if you think back to when you did BGCSE chemistry, there were these calculations that you had to do. They were called they were discussed under the name or moniker stoichiometry. So that is a simplified version of dimensional analysis. So the thing that you have to think about, and that should be spelled chemistry. So excuse that. Um, Things you have to think about. You have to look for what are you given? What is in your hand? What is on the paper? What values have you been given to solve this problem? Solve for. What are you aiming for? What value or specific parameter are you aiming for? The other info in the problem, that's something that you want details of the problem. Those are things you want to think about. That's step 3. The conceptual plan. How will you solve the problem? The solution. What will you do to solve that problem? And then you check it out. You check it with your intuition, your fundamental understanding of the concepts. You're going to check it out with that, and you're going to solve the problem. So step 1, you look at your given info. Step 2, you solve for a specific variable. Step 3, you look at the other info. You keep the problem in context. Step 4, you come up with how you're going to solve it, your conceptual plan. Step 5, you give your solution. Step 6, you check out your solution and see if it makes chemical sense. So this is a general idea. You look at the number of objects over 1 times the related object over one object and decide SI unit over the unit. So this is how you would generally solve a metric problem. So let's think of an example. Say for example we want to solve for the length of a group of hydrogen atoms. So in this basic step, we use the number of objects given in the problem as the basis for conversion and solutions. That is going to be step 1. So the number of atoms in 1 mole is Avogadro's number 6.02 times 10 to the 23rd. Those are the number of atoms in 1 mole of hydrogen. And then we think of a ratio. So we have the 1 mole, we have the number of atoms of the object. So as we said earlier, the number of objects, we know the number of objects. Now we're going to relate it to something over one object. So if we want to solve for the length of a group of hydrogen atoms, we look at 1 mole, 6.02 times 10 to the 23rd atoms, times 212 picometers over 1 atom. And then from there, we discuss or we note how long is that picometer? How long is a picometer? And so we know that 10 to the 12 picometers equals 1 meter. And we calculate it out and we get 1.28 times 10 to the 8th meters. Sorry for the missing unit. We get 1.28 times 10 to the 8th meters, and that's the length of a group of hydrogen atoms if they were all placed in one line together. So what is a derived unit? So we just discussed how you solve for metric analysis problems, and I will give you some of those to solve. What is a derived unit? A derived unit is a combination of other units. Examples of derived units are those for force, which is kilogram meter per second squared, which is force is equal to mass times acceleration. So kilogram is the unit for mass, meters per second squared is the unit for acceleration. You multiply those two, you get kilogram times meter over second squared. And for momentum, momentum is mass times velocity. And from that, we get that the unit for that is kilogram meter per second. So what is that? Now we're going to talk about, we're still discussing foundations. So we're going to now talk about what is an intensive property. An intensive property, intensive, independent of the amount of substance. So an intensive property is a property that's independent of the amount of substance. And it involves, or an example of that is going to be density. So it's a characteristic property. It doesn't change depending on the amount that you have. It is the same no matter what what amount of it you have. An extensive property is a property that does depend. So extend does depend on the amount of substance. An example of that is going to be mass. The mass of substance is dependent on the amount that you have. So, at the still talking about foundations, these are things I need you to understand. This is the language, the jargon, the foundational ideas I need you to understand for us to do chemistry this semester, regardless of the format. I need you to understand this. What type of substance is a compound? A compound is an example of a pure substance. So compounds of pure substances, an example of a pure substance is going to be sodium chloride, pure sodium chloride, crystalline sodium chloride. That's a compound made up of two different elements, and that is a pure substance, and it is a compound. What type of substance is an element? An element is a pure substance made up of one type of atom. So for example, sodium metal is an element. That's a pure substance. A, a sodium metal is an element. So what type of substance is carbon monoxide? I know you've heard of carbon monoxide poisoning, which is dangerous if you don't have proper facilities. What type of substance is carbon monoxide? Carbon monoxide is also a pure substance as a compound made of carbon and oxygen. What type of property is color? Color is a physical property and does not necessarily require the intermolecular bond breaking to be observed, although some electronic transitions do result in color changes, and that's where we get the atomic spectral series from. So it's interesting how they interplay. What are the rules for significant figures? So if you look at the animation, we can see that all non-zero zero digits are significant, interior zeros are significant, leading zeros are not significant, trailing zeros after decimal point are significant. Trailing zeros before decimal point are significant, and avoid unclear notation such as trailing zeros before an implied decimal point. So let's keep going. What is an example of a game that combines the ideas of precision and accuracy? Darts. Darts is an example of a game that combines the ideas of precision and accuracy. Now let's talk about some more foundational concepts. We're going to talk about conservation laws. These are important to understand. These are foundational things that we're reviewing before we get into wave particle duality. These are things I need you to understand well. So rewatch this video if you need to. Rewatch it again. I recommend you do it. Or at least watch it twice and take detailed notes. And design this in such a way so that it can be integrated, it can be engaging, it can be stimulating, it can be well understood. What are the foundational concepts I need you to know for this semester? So what is the law of conservation of mass? The law of conservation of mass states that the total mass of a substance in a closed system does not change, where there is neither generation or consumption in the system. Essentially, it says for mass, mass is not created or destroyed. So what is the law of conservation of energy? Conservation laws, which are noted in the animation, they are classical. Conservation laws they are, or for the law of conservation of energy, energy is never created or destroyed. It's only transferred from one form to another. Heat energy to light energy. So keep that in mind. Now let's talk about some key scientists. I need you to know a few people. We gotta know a few people before we really delve deep into wave particle duality, because there's another group of people that I want you to know about. So who are all the scientists that have been presented so far? Why are their contributions so significant to chemistry? So Joseph Proust is important. I need you to know, and I will give you a worksheet with these people on it. Antoine Lavoisier is important. Um, Joseph Proust is important. John Dalton is important. Albert Einstein is important. All of these people. Let's talk about. For example, John Dalton. His atomic theory was pivotal to um, understanding mass, and understanding key ideas with atomic mass. Even though it had to be refined, his ideas were fundamental, whether it be from the original founder or the original person who described Mahadan's compositional units to John Dalton. It's important. So what is the law of definite proportions? And this is where Joseph Proust comes in. The law of definite proportions refers to substance composition and classically states that specific compounds are always made of the same elements in the same ratio. This is true. H2O is H2O. It has a definite proportion. Two atoms rather, of hydrogen with one atom of oxygen. And you see this in the balanced chemical equation. The balanced chemical equation is proof positive that the law of definite proportions is true in many instances, or in all instances, at this level. What is the law of multiple proportions? This is where John Dalton comes in. The law of multiple proportions basically states that two atoms, C and D, when combined together for a compound, the ratio of D to the one compound, in the one compound rather, to the ratio of D in the other compound will be a definite ratio. So for example, let's make this more concrete. So law of multiple proportions states basically two atoms. So let's talk about hydrogen and oxygen. So let's think about that. When combined to form a compound, water, the ratio of oxygen in the compound, 1, and the ratio of oxygen in another compound will be a definite ratio. So for example, ratio of oxygen in water to the ratio of oxygen and magnesium oxide would be a definite ratio. It would be 1 to 1. What made Dalton's atomic theory significant? So Dalton, as you see on the graphic, some of his ideas which have been refined. Each element is composed of tiny particles called atoms. All atoms of the same element have the same mass. Atoms combine in simple whole number ratios to form compounds. And he said that atoms of one element cannot change into other atoms of another element. We know that that is not the complete story. Number 4, the tenet of his atomic theory is not the complete story, because as we learned later on after John Dalton, with the Curie family, Marie Curie and her daughter Irene Joliot Curie, we learned that there's a thing called transmutation, in which you have one element being converted to another element, and that involves radioactivity and radioactive decay. But let's keep the big picture in mind. What made his atomic theory significant? His ideas have been adjusted, but his theory is significant because although some changes were made, his work laid a good foundation for chemistry research at the time and today, and understanding chemical reactions. Ladies and gentlemen, this shows the iterative nature of science, that we are constantly learning and developing new ideas using a dynamic scientific method. Who was J.J. Thomson? See, we're talking about people now. These are people you need to know about, people you need to meet, who you need to discuss, who you need to talk about with your colleagues. You need to understand what did they do. Who was J.J. Thomson, and what were some of his experimental findings on cathode rays? J.J. Thomson, whose work with cathode rays built up to the discovery of the electron. He was an English physicist who made profound discoveries on cathode rays and led to the discovery of the electron. He also proposed the plum pudding model, wherein he hypothesized that negatively charged electrons were small particles held within a positively charged sphere via electrostatics. So he proposed the Plum-Pudding model, which is a common idea that you're introduced to when you're first discussing periodic properties. And his work led to the discovery of the electron. There's also Robert Millikan, who performed the famous Millikan oil drop experiment, which aided in determining the fundamental charge of a single electron. So who was Marie Curie? Marie Curie is a significant scientist that everyone should know about. She was a female scientist who won 2 Nobel Prizes, her and her husband. And her children also won. One of her children also won a Nobel Prize. The Curie family's work on radioactivity led to a lot of progress, achievement, and identification of alpha particles, beta particles, and gamma rays. She won 2 Nobel Prizes in chemistry. And let's not forget the work of Rutherford, whose nuclear theory was foundational. He described most of the atom's mass and all of the positive charge as posit in the nucleus, or placed or situated in the nucleus. Who was Ernest Rutherford, and what were some components of his nuclear model? So Rutherford was a leading nuclear physicist whose work led to the further development of atomic theory. He served as the director of Cavendish Laboratory at Cambridge University. His nuclear theory had ideas around the following. For the atom, most of the mass and all of its positive charge is in the nucleus. Most of the volume of the atom is empty space, and the number of electrons and protons is equal to maintain an electrically neutral atom. So what does that mean? Most of the volume of the atom is empty space. That points, or that gives you an idea that the massiveness of the atom is situated in the nucleus. The mass of electrons is negligible in this course by convention. However, the mass of the neutrons is 1 atomic mass unit, and the mass of the proton is 1 atomic mass unit. The number of electrons and protons is equal, typically the case in a stable neutral ground state element, and those are equal. Okay, who was James Chadwick, and what did he discover? James Chadwick was a British physicist who observed that the mass of the atom that was unaccounted for was due to the neutrons within the nucleus. His work led to the discovery of neutrons. So what is the mass of a proton and what is its charge? Take a few seconds, guess, think about it. Protons have a mass of 1.67 times 10 to the minus 27 kilograms, or 1 atomic mass unit. We can discuss the relationship between kilograms and atomic mass unit in a problem-solving session. Remind me. Also, a proton has a relative charge of positive 1. What is the mass of an electron and what is its charge? Electrons have a mass of 9.1 times 10 to the minus 31 kilograms, or 5.5 times 10 to the minus 4 atomic mass units. Also, a electron, excuse that, has a relative charge of minus 1. So I want to just narrow in on some quick ideas from this animation. Niels Bohr was very important, or is very important in general chemistry. His idea of atomic spectroscopy involved the study of electromagnetic radiation emitted and absorbed by atoms. He postulated that each stationary state or orbits are fixed or quantized. He understood that electrons have stability, and when transitioning between orbits, radiation is emitted or absorbed. Although his model was initially successful, it was not a complete explanation, and it was replaced by a more developed quantum physics theory that addressed the wave-particle duality. And that's very important. That kind of leads us into the idea of wave-particle duality. So what is the mass of a neutron and what is its charge? just before we transition into wave-particle duality, let's just continue going over a few foundational concepts. The mass of a neutron has a mass of 1.67 times 10 to the minus 27 kilograms, or 1 atomic mass unit. Also, a neutron, rather, has a relative charge of 0. What are the symbols for atomic number and atomic mass? The symbol for atomic number is Z, and the symbol for atomic mass is A. So now let's discuss uh, the wave-particle duality idea. So before we get to wave-particle duality, I want to introduce you to the Schrodinger's cat thought experiment. Before we get to wave-particle duality, I want to introduce you to that, and then we'll discuss wave-particle duality. But actually, before we get to showing you the images and describing it to you in the format we were just discussing it, I would like to show you a reference text that you can use as you do your studies. So this is Chemistry LibreText, and this is a very good resource, students. Chemistry LibreText provides you with a variety of different textbooks and resources that you can use to empower yourself to learn. So this is the Schrodinger's cat thought experiment, and it basically gives you an idea as to quantum strangeness, or the idea that quantum mechanical behavior is strange. It introduces the idea that things that equal probability of events occurring, but under observation, one is definite, or one is discretely known under observation, really known and observed. So let's go back to the PowerPoint. Now I want you to watch this video, and I'm going to turn my camera off and allow you to watch the video, and then we will continue with the lecture after the 2 videos.
In Brussels, and he came here and was admitted on that day as a in November the 9th, 1933, the great Austrian physicist Erwin Schrödinger came to this room, this office where I work, the office of the president of Magdalen College. Schrödinger had been at the Solvay conference in Brussels, and he came here and was admitted on that day as a fellow of Magdalen College, using Latin phrases that we use to the present day. After the ceremony, in this room, the phone rang, and it was from the Times of London. And the Times of London said that Schrödinger had just been awarded the Nobel Prize. So he was heard he'd won the Nobel Prize in this room, and next day in the Times and the Telegraph newspapers it stated that Schrödinger of Oxford University had won the Nobel Prize, even though he'd actually been employed before at the University of Berlin. What did Schrödinger win the Nobel Prize for? Well, it was for a paper he wrote in 1926 when he introduced his famous Schrödinger equation. Up to that time, the theory for explaining the energy of electrons in atoms had really been due to the famous physicist Niels Bohr, who'd come up with a theory for explaining the spectrum of the hydrogen atom, the electronic spectrum of the hydrogen atom, and fitting the energy levels with his own formulae. But Bohr's theory didn't work very well at all for other atoms or even for molecules. It didn't seem to be a general one. What Schrödinger did is he came up with a general equation that worked for the hydrogen atom and worked for predicting not just the energy levels of the hydrogen atom, but also like the intensities of the spectral lines, whether the lines in the spectrum are intense or not. He could predict that intensity, and that was new. Not even his collaborators or the people who were competing with him, like Heisenberg, knew how to do that, and Schrödinger did it with his equation. And then Schrödinger, in the same year, realized that he could apply his equation not just to the electronic energy levels of the hydrogen atom, but to other problems like the vibration of a harmonic oscillator, like to the rotation of a diatomic molecule. The same equation could be applied and gave the results that agreed with experiment for those sorts of problems. And then Schrödinger realized his equation could also be adapted not just for simple processes, but for processes that depend on time. So in fact, there are two Schrödinger's equations, what's called the time-independent equation and the time-dependent equation. But why the equation became so significant is that suddenly many scientists around the world realized that not only did it work for the hydrogen atom, it worked for all atoms and all molecules in principle. And that means it had remarkable applications to nearly everything you can see. Depends on atoms and molecules, and Schrödinger's equation can be used to calculate all their properties. And if you solve his equation very accurately, you get essentially the right answer. So it was a very powerful theory that came out of Schrödinger's great work in 1926 for all atoms and molecules. Now the problem is, though, his equation was quite complicated mathematically and very difficult to solve for anything more complicated than the hydrogen atom. Even for the helium atom, it involved quite a lot of difficult integration and differentiation and so on. And so it didn't really change science so much in the very early days. But where the big change came with Schrödinger's equation was when computers came along. It was then possible to use computers to solve his equation and do that really accurately as time has gone on more and more. And that means Schrödinger's equation can be applied to more and more complicated systems, atoms, even now even to solids, materials, and also to problems of biological importance. You can do calculations with Schrödinger's equation, for example, on proteins, on enzymes, on DNA, and so on. And so it's become, in the modern world, an extremely powerful theory. It's the theory that underlies the whole of chemistry, molecular biology, material science, understanding the properties of materials. You can do calculations with Schrödinger's equation, and many people do that. Even in geology, you can calculate the temperature at the center of the Earth using variants of Schrödinger's equation. And so in the 21st century, it's become really almost the essential tool for doing simulations on atoms and molecules. The other method, before Schrödinger, was developed by Isaac Newton, Newton's laws. And you could simulate atoms and molecules using Newton's laws, but those don't include, crucially, quantum mechanical effects. such as tunneling, such as probability. Newton's laws just don't work for atoms and molecules, but Schrödinger's equation does. So Schrödinger came here in 1933, and he came to work here in Oxford. He was a fellow in my college. He lectured at the University of Oxford on the quantum theory, but he wasn't very happy here. He had an appointment which was almost like a postdoctoral assistant. After being a top professor in the University of Berlin, he had an appointment that was just renewed every year, funded by ICI, the chemical company. So he wasn't very happy. And he was here just for 3 years, and he missed his great friends in Berlin. He was very friendly with Max Planck, the person who discovered quantum theory. He was very friendly with Einstein, who was also in Berlin in the 1920s. He missed his friends. And in the end, he was unhappy here, and after 3 years, he decided to move back to his home country of Austria, where he was given an appointment at the University of Graz in Austria, and also another appointment at the University of Vienna. And that's where Schrödinger went. He'd left Berlin in 1933 because he wasn't very happy with the politics that was going on in Germany at the time. Science and politics in those days really intermixed. He didn't like what the Nazis were doing. So he came to Oxford. But then he made the big mistake of going to Austria, and he didn't realize that there were going to be problems in Austria because Hitler's troops marched in 1938. And Schrödinger had to escape from Austria.
So now we will continue with the lecture. Let's look at video 2 and then we'll continue with the lecture.
Austrian physicist Erwin Schrödinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, "What is the state of the cat?" Common sense suggests that the cat is either alive or dead, but Schrödinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrödinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrödinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior.
And this is what's referred to as the Young split experiment. We will get to that later on in the semester. This is pointing to and hinting to one of the big ideas that we're going to discuss next lecture, which is wave-particle duality.
A set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between.
And we account for this. This basically is describing what we describe as probability distribution, which basically is a fancy way of saying electrons exist over a cloud, over a region of space, in not a one specific position. And this also hints at the idea of uncertainty, Heisenberg uncertainty, which basically describes that you cannot know with the same degree of accuracy the momentum or the position and the momentum of an electron at a specific point in time with the same level of accuracy.
Between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor, or an insulator, or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
So this, ladies and gentlemen, this is a description of the Schrodinger's cat thought experiment. We will discuss this before the lecture ends. However, just make on a quick note, feel free to go to YouTube and get more of these TED videos. If you find a video that you think is beneficial to the class, you can send me an email with the link, and I will, if it's an educational appropriate video, educationally and age appropriate video, I will look at it and determine whether it's appropriate for the class discussion at the time. So let's go back to the lecture. Just before we conclude, I want to discuss Schrodinger's cat thought experiment, and then we will conclude this lecture for today. Now, just in case you didn't get it the first time, I want to explain it to you from the animations I've designed for this class. So, with this, we have Schrodinger's cat thought experiment. In the thought experiment, you put a cat in a steel chamber for an experiment, and this whole scenario is just an imagination or an imaginary experiment. In the chamber, there is radioactive material and a mechanism that, upon emission of an energetic particle by one of the radioactive atoms, a hammer breaks a flask of poison and results in a dead cat. Yeah, this is amazing. If the chamber is closed and you do not observe what is going on, there is equal probability that both the cat is dead and the cat is alive. by virtue of the system being observed. So let's Bahamianize this thought experiment. So let's begin. Imagine there was an oil and beach spill by a pond in Inagua. The area is enclosed by a mind your business fence, so you must enter the area to observe what occurs. If the flamingo in the area drinks from the pond, the flamingo will die in the area. If you are not around to observe what occurs in that pond area, and the pond area is enclosed, the flamingo has equal probability of being dead and being alive by virtue of the fact that the system is not observed. So what does this point to? Don't get lost in the details, but what does this point to? This points at quantum mechanical behavior and uniqueness and the strange nature of it. It also hints at how quantum mechanical behavior does not exactly transfer for an understanding of macroscopic behavior. There is uncertainty and indeterminacy. Yes, the behavior of electrons is strange. And as we conclude, I want to remind you, many of these scientists met at the specific conference called the Solvay Conference, where a lot of brain physicists meet. And if you look at the picture, there's a characteristic picture of many of the scientists in which in this one photograph, Albert Einstein, Heisenberg, all the others, and that was at the Solvay Conference. Next lecture, we will discuss the wave-particle duality and other scientists. Once again, thank you again. I'm excited to be teaching you this semester. I hope we're able to accomplish a lot, learn a lot. Remember, I expect you to be hardworking, ethical, and responsible. Remember, you are not alone. We are in this together. This is an academic community. However, you are responsible to be ethical, hardworking, and a good potential scientist. Be encouraged, be inspired, and see you next time for General Chemistry 1 lecture.